Okay, good morning, everyone. Let's continue with our analysis technique. Today we'll look at node voltage analysis. So, okay, node voltages and mesh currents. These are the final two big analysis techniques in this chapter, but there's still a long way to go. These build off of the techniques that we have learned previously. Now, Ohm's law, KCL, KVL. We'll use those to write out equations which have unknown variables. And the unknown variables, in our case, are basically the voltages and currents that appear in the circuit. So, node voltage analysis and mesh current analysis, again, the point is to solve for the unknown voltages and currents. The previous techniques that we've looked at work for simple circuits or for like circuits which have only one source and circuits that are reducible down to one single component. But these techniques can be applied to any circuit. So, node voltages and mesh currents. In this example schematic, well, what I'm going to talk about is how we can express voltages, component voltages in terms of node voltages. So in this example circuit, there are some notations and some marks already given to us, okay? These are assumptions that we would make when we were trying to solve for an unknown circuit. So for instance, voltage polarities are given to us, right? Right here and right here, okay? These are assumptions that we would make when we begin analysis. Plus the nodes are labeled A, B, C, D. So those are the nodes that are present in the circuit. A, B, C, and D. There are mesh currents, but we will not look at those just yet. Not looking at those yet. So don't worry about IA and IB. Okay? Don't worry about IA and IB. Okay. Let's still take a look at the nodes. A, B, C, and D. What do we see? A at the bottom is connected to ground. Now, even if the ground symbol is not present or is not given to us, don't worry about it. It doesn't change our analysis technique. Okay, it doesn't change our analysis technique. What I want students to focus on is basically the resistor voltages V1, V2, V3, and V4. Okay, R3 is not written, but this resistor is R3. Okay, so we have 4 nodes and 4 voltages, VA, VB, VC, and VD. Each of these voltages correspond to the voltages present at that node. But voltage is the difference in electric potential between any 2 points, right? You measure voltage between 2 points. There has to be a reference point. So the first thing we do in node voltage analysis, after identifying the nodes and labeling them, is to choose a reference node. Again, voltage is the difference in electric potential between any 2 points, meaning you're measuring the potential, electric potential at one point with your reference at another point. So the first step in node voltage analysis is to choose a reference node. This reference node is the common reference for all other node voltages. In this example, VA at the bottom is chosen as the reference. VA is chosen as the reference node. sorry, A is chosen as the reference node. And so VA, if you're measuring the potential at A with reference to itself, the obvious answer is that VA would be equal to 0 volts, which is noted right here. Okay, noted right there. VA is equal to 0 because it is a reference node. So important point, you choose a reference node. Doesn't matter where it is in the circuit. It could be top left, top right, in the middle, at the bottom of the schematic. It doesn't really matter. You choose a reference node. We'll talk about more later on when we get to the example, but it doesn't really matter which node you choose as the reference node. But once you choose that node, the value for that node for that analysis is equal to 0. Okay, for that analysis. If you choose node B as your reference, then VB would be equal to 0 for that analysis. You can take the same circuit and solve it by choosing two different nodes, meaning two different analyses, separate analyses, okay? Not the same one. You can solve it by choosing a node as a reference, and you solve it again using a different node as a reference, but each analysis technique stands separately, and you would obtain the exact same answer at the end of your analysis. So again, the important point is you choose a node as a reference, that node would be equal to 0 volts. That's it. Now, once you have your reference node, you can express all other node voltages as measured with regards to that reference node. So VB is actually VBA. The A is implied. Okay, the A is implied. So VB, the node voltage B, expressed in terms of the two subscript notation, is VBA. Okay, VBA. Again, because A is a reference node, it has a potential of 0 volts, and so it's VBA. If you were to take the multimeter, you would put the positive reference, positive lead at B and the negative at A. Everyone with me so far? And so similarly, I can say VC is VCA and VD is VDA. Okay, two subscript notation. Now, resistor voltages. Here we are already given the names V1, V2, V3, and V4. The goal is to express each resistor voltage in terms of the node voltages. Okay, in terms of the node voltages. Oh. Even before that, actually, let's look at the power supply. Where is the power supply connected? Between nodes B and A. Nodes B and A. And the power supply has a polarity. It's already given to us, plus at the top, minus at the bottom. Meaning, we already assumed or is given to us that VB is at a higher level or higher potential than A. So I can write VS is VB minus VA. VB minus VA. VA is equal to 0. So I can write my voltage at node B is simply equal to the supply voltage VS. And that leads me to the important point of saying that if there is a voltage source present in the circuit, if you choose one end of that source as your reference, you automatically have a value for the node voltage at the other end of that power supply. Again, voltage source Vs is connected between nodes B and A. Between B and A. So if we choose A as a reference, we automatically have a value for VB. If we choose, as an example, if we choose B as reference, then VA would be equal to, magnitude would remain the same, but the sign would flip. VA would be equal to VS, but now it would be minus. Just because the positive end of VS is connected to B and the negative end is connected to A, meaning A is lower than B. So if B is my reference, B has a value of 0. So I would write it as Vs would be equal to, the explanation for this would be Vs is equal to VB minus VA, but VB is 0. And therefore, is equal to minus Vs. Does that make sense to everyone? Right? So when you're choosing a reference node, feel free to choose any node in the circuit, but it would make things easier. It would make the analysis more efficient if you choose one end of the power supply. And typically, if it's a negative end of the power supply, or not power supply, negative end of the voltage source as your reference node. It just makes things easier. All right, 10-second pause. Let me know if you have any questions. By the way, node voltage analysis technique has been introduced in class. So I would expect students to actually open up the homework and actually take a look at it, get started on the tutorial, which is extra credit. And then, of course, when I go to the example problems, I would assign a due date for that homework. Yes. Oh, VB is not. This is just as an example. So if VA is a reference, then I can write VB is equal to VS. Here, A is the reference. And the example was if I use B as the reference, then I could write Vs is equal to minus Va. Whichever end you choose. If you choose the negative end, the answer at the other node is positive. If you choose the positive end as the reference, then the other end of the power supply is negative. Anyway, so once we have that, we can express each resistor voltage in terms of the node voltages. The reason is each resistor has two terminals. As an example, R1 is connected between B and C. From my assumption, I've already noted that B is at a higher potential than C. My current is going from left to right. So my current is going from left to right. B is at a higher potential than C. I can write voltage across resistor R1 is VB minus VC. Okay, VB minus VC. Voltage across the resistor R1 is the difference in node voltage at either end of that resistor. VB minus VC. And this is, again, this is the important step. This is one of the first steps when we write out the expressions. Okay, we're expressing each resistor voltage in terms of the node voltages appearing at either end of that resistor. So V1 is VB minus VC. V2 is VC minus VA, which is this voltage right here. And similarly, V3 and V4. Any questions? And again, things become more clearer as we look at examples and we go further into this technique. Okay. Move on. We have resistor R given to us, current going from the left to the right, and terminals A and B. A is on the left, B is on the right. If my current is going from the left to right, where is the polarity of the voltage? What is on the left? Plus or minus? Current always goes from high to low, from plus to minus. Point of entry is always plus. So this is plus, this is minus. So VA is higher than VB. Remember, this is an assumption you would make when you were trying to solve a problem. The current direction may or may not be given to you, but if you're assuming the current flowing in this branch is going from left to right, then logic dictates the voltage at VB would be higher than C. So I would write VR, voltage for my resistor R, is VA minus VB. From Ohm's law, I can write current I is equal to VR over R, substitute, and I get an equation for I, or that current, in terms of the node voltages. Does that make sense? So that's one of the steps. We express the resistor voltage in terms of the node voltages. We apply Ohm's law, and we have an equation in terms of those variables. Well, not an equation, but an expression in terms of the node voltage variables. Yes. Sure. No. So I'll expand on the explanation and then in just a couple of slides. Yeah. So at this point, all the currents and all the voltages are unknown to us. We have no idea. We're just making assumptions of the current directions and then writing out equations. And that's when we'll find out the values. So where was I? Let's see. Oh, so this is done. Now we expand it and apply it to this example right here. Okay. So the point of node voltage analysis, again, node voltage analysis or mesh current analysis, is to solve for unknown quantities, right? In this case, our unknown quantities are node voltages. So they are variables. And we will write equations to solve for those unknown variables. If we have one unknown variable, we need one equation. If we have two unknown variables in our circuit, we need two equations. Three unknowns, three equations, and so on and so forth, right? So in this case, we have 4 nodes, VA, VB, VD, and VC. Going back to the slide, I said we have 4 nodes in this slide. So 4 unknown variables, right? So we need 4 equations. But VA is a reference, or one node out of those 4 would be a reference node. So we know that that would be 0 volts. And then B is connected to a voltage source. So we would know the value for B. So out of 4, I would have the value for the reference node. I would have the value for the voltage source. I'm left with only 2 unknown variables. I only need to write 2 equations to solve for these 4 nodes, as we'll see in an example later. So 4 nodes right here, 3 resistors, R1, R2, R3. Current directions are given to us. I would mark out the voltage polarities, plus, minus, and plus, minus. Again, those plus, minus only refers to the voltage of that resistor or that resistor voltage. It doesn't refer to anything else, okay? It is not talking about the relationship between the node voltages itself. These plus, minus signs, they're only referring to that individual resistor. Does that make sense to everyone? Right? Do not get confused with node voltages. So I have VA, VB, VC, and VD. This is not a large circuit, just a small example. What I want to do is I want to generate an equation, and in node voltage analysis, the way we generate the equation is by applying KCL. Voltage analysis, you would apply KCL, current law. Okay. So I'd apply KCL at node B. KCL at node B. I have I1 entering the junction, and I have I2 and I3 leaving the junction. Right? You apply KCL to generate this equation. Once I have that, I'm going to express. So this is, sorry, not ohms, KCL. And then I apply Ohm's law, and I will express each current in terms of the resistor voltage and the resistor value. And so this would be VR2 divided by R2. And this would be VR3 divided by R3. And this, of course, is from Ohm's law. Now you see where this is going, right? We apply KCL, we have our equation, then you express each current in terms of the resistor voltage. And then the next step after that is to express each resistor voltage in terms of the unknown node variables or the node voltages. So VR1 in this case is going to be VA minus VB. And R2 would be VB minus VC. And R3 would be VB minus VD divided by R3. VR1, voltage across resistor R1. So it's VA minus VB. The reason is because my current is going in this direction from left to right. So I'm assuming that VA is going to be higher than VB. And that's why I said, do not be confused by the plus and minus sign. Single node cannot have 2 signs. The signs are simply noting the resistor voltages. Okay. So current going in this direction. So A is higher than B, and then B is higher than D. 10-second pause, think over it. Let me know if you have any questions. Yes. So this is just a smaller step, and then the next example, we'll see how that works. Yeah. So these are the fundamental steps we need to apply in order to generate those equations. All right, any questions? Any other questions? Okay. So to recap, as a first step, we identify all nodes in the circuit and you choose a reference node. The reference node, of course, will automatically have a value of 0 for that analysis. Okay. If there are 4 nodes in the circuit, you could analyze the circuit 4 different times, as practice if you want to. And you can choose a different reference node every single time. But every single time you choose a reference node, that node will have 0 volts as its value, just for that analysis. Then we assume and assign currents to all branches, meaning all resistors in the circuit. And this assumption, of course, is based on logic. Apply KCL at each node, write out the equation. Apply Ohm's law and express each current in terms of the resistor voltage. Typically, some students like to skip this step. I would say strongly advise, do not skip this step. If you do, you need to make sure you're an expert at writing out the equations. And then finally, of course, express each resistor in terms of the node voltages. Your node voltages are the unknown variables. So you solve for these unknown variables. As I said, if you have one unknown variable, you would need one equation. If you have two unknown variables, you need two equations, and so on and so forth. And once you have those equations, you can solve them any way or any method you want. You can use your programmable calculators. I solve them manually because I don't have a programmable calculator. My calculator is from the 90s. It still works. Again, feel free to choose any method you want. All right, questions? Okay, let's look at this example then. Solve for all branches, all branch currents and node. Branch simply means the component that is connected in that single line. All branches and node voltages. So when it asks us to solve for node voltages, it's asking us to solve using node voltage analysis. Okay. I like this example because one current source going up, the other current source going down. Doesn't have a voltage source in there. Both of them are current sources. Okay. So what's the first thing you see? What do we see about R2 and R3? They're in parallel, so we can reduce them. So the first step, I would reduce it to R23. And I would say R23 is a parallel combination of R2 and R3. So it's 1000. And you can take your calculators out and go and solve this as I go along. And this one comes out to be, I think, someone solve this and let me know if I'm right. Anyone? All right, thank you. I1 and I2. All right, so the first step, we combined parallel resistors R2 and R3 into one single resistor. Just makes our job easier. Now, how many nodes in the circuit? No guesses, I mean, no penalty for guesses, so you can go ahead and guess. 3, 4, 5, 6. All right, so we got 1, 2, 3, 4. 6 was a popular answer even in the previous section. Anyone with 4? 4. Anyone with 5? Going once, going twice. All right, let's see. Connected here, connected here, connected here. 1, 2, and 3. Take 10 seconds and think over it. Do you see that now? Again, always keep in mind, a node is a junction, but the junction could be very, very short or could be very, very long. On a circuit schematic, it could be a tiny dot. It could be a short line or a very long line, but it is still a connection. It is still the exact same node. You could take, again, an example of the power extension cable. Take this orange power extension cable, 100 feet long, plug it into a wall outlet. You would expect to get zapped if you stick your finger at the other end, right? It's the exact same node. So it doesn't matter how long it is, doesn't matter how many dots you see on a schematic, it is still the exact same node. So 1, 2, and 3. Some things are not as obvious, because even if they are staring at us in the face. The first few times I solved this problem, I never ever thought to combine R2 and R3 together until a student actually pointed it out in class. I just never thought of it. I would solve it by applying different, R1, R2, R3, R4. And then a student pointed out hesitantly, like, isn't that the same resistor? We could combine it. And I was like, yeah, you're right. So anyway, even after years of practice, some things don't strike us. But again, the point is, even if you would take in it like 4 nodes or 5 nodes or 6 nodes, you would still end up with the right answer. You would just have to do a bit more work, because now you have more nodes, you're going to write more equations, but your answer would still be correct. And that's the point. Okay, so I'll go a little bit faster now. We got 3 nodes. I'm going to label them A, B, and C. There's no voltage source here. I'm just simply going to choose the bottom node as my reference. And I'm going to say reference node. And therefore, VC is equal to 0 volts for the purposes of this analysis. Okay. Now is the time to choose the direction of the currents. And the reason I find it interesting is because I2 goes down. So which direction should we choose? It's an assumption. You can make an assumption any way you want. Now, since I1 is going up, I always tend to start from the left side of the circuit schematic. And I would say current going in this direction. And if current's going in that direction from left to right, I would say it's also going down R1 and going down R4. Make sense? I could also choose I1 going, since I2 is coming down this way, I could choose it going up. There's no wrong or right assumptions. It's an assumption, right? So we simply just make an assumption and we proceed. So just to make an example at the end, you will realize that the assumptions doesn't make a difference. So let's choose this going down and going towards the right. So if my currents are going in this direction, point of entry is always positive. So the voltage drop across each of these resistors will be in this direction. Again, remember, these are assumptions. I'm simply assuming the directions, and then from those assumptions, I'm applying the polarity for the voltages. This is R1. This is R2. I will label this IR1 and IR2 and IR23. Okay. Make sense? Any questions so far? Oh, yeah. Yes, R4. Thank you. This is R4. R4. All right. So now, yes. Oh, so it's this bottom node right here. Okay. This circuit, I could also draw it like this. Let's see. So all of these converge right here. That's the bottom node C. And just got messy. This is A and this is B. So even though circuit schematic is drawing out differently, the entire connection is just wires. As long as there are wires connected to it, the entire thing is a node, is a junction. Okay, so reference node C, I have VA and I have VB. I'm going to apply KCL at node A. At node A. So KCL at node A gives me current I1 entering the junction and current IR1 and IR2 or IR23 leaving the junction. Okay, KCL. Current I1 entering the junction and IR1 and IR23 leaving the junction. Then apply Ohm's law. I1, of course, is given to us. It remains the same. IR1 becomes VR1, voltage across R1 divided by R1. And IR23 becomes voltage across that resistor VR23 divided by R23. The voltage notations are not noted in the schematic, but again, I would, at this point in the class, students should be familiar with that. If you see a component R1 and you see VR1, it refers to that voltage for that component R1. So applied Ohm's law. Now I express each resistor voltage in terms of the node voltages. And so I1 would simply be VA minus VC divided by R1 plus VR23 is between A and B. So VA minus VB divided by R23. At this point, plug in all the known values in the equation. I1 is 10 milliamps, 0.01. VA is unknown. VC is 0. R1 is 1000. VA minus VB divided by 166.667. Now at this point, yes. Mm-hmm. Oh, you're right. You're right. That's elementary error. Someone should have caught that. R1 is 1000, R2 is 2000. So R23 cannot, wait, no. So it's 2 and 10, not 1 and 2. Yeah, 2 and 10. So R2 and R3 in parallel. Okay. You confused me for a second there, for 5 seconds. Let's see. Where was I? Oh, yeah. At this point, after you plug in the values, you can solve any way you want. The way I like to do it is I like to get rid of all the numbers in the denominator and I bring it upstairs. And so I multiply everything by 1000 and that gives me 10 is equal to VA plus what is 1000 divided by 1666 0.5999. Does everybody have the same? So I would have 0.599 VA minus VB. And then rearrange the terms, I would get 1.599 VA minus 0.599 VB is equal to 10. And this is my first equation. Let's take a 10-second pause while you write it down, think over it. Let me know if you have any questions. No questions? Okay, then let's write KCL, KCL at node B. At node B. KCL at node B gives me, what do I have? IR23 entering the node and R4 and I2 leaving the node. Okay. So IR23 entering the node. And IR4 and I2 leaving the node. Apply Ohm's law. I have VR23 divided by R23 and IR4 is VR4 plus I2. Expressed in terms of the node voltages, this still is VA minus VB divided by, I'll plug in the values, 0.667 and VR4 is simply VB divided by R4. R4 is 2000 plus I2, which is 0.05. Multiply everything by 2000 and I obtain, what do I obtain? 1.199 VA minus VB equals VB plus 100. I rearrange the terms and I get 1.199 VA minus 2.199 is equal to 100. And this is my equation number 2. Oh, it should be VB. S. Yes. So some is just force of habit with me. I like to take like 3, 4 decimal places instead of rounding up. I just take it that way. Sometimes the answers do get weird. So if students take 2 decimal places and round up, that's fine. As I said, it's just force of habit that I keep doing it. You're talking about this first one or the second one? Yeah, it come out to be 1.12, sorry, 1.2 and 2.2. And you can just solve it that way. It's fine. I don't expect students to do this. I've been doing this for like, 3 decades. So it's just force of habit that's hard for me to break. In one of the homework problems, there was an example where if students took 2 decimal places versus like 3 or 4, they would have a slightly different answer. So you do get slightly different answers if you take, less digits. Any other questions? Okay, go ahead and you can go ahead at this point and solve using any method you want. You can solve using a calculator, or like me, you could solve it manually by hand. If you have a programmable calculator, please plug these equations in and let me know what answers you receive. So let's see. Wolfram alpha. Anyone? One point. My notes are somewhere in my office, and I haven't been able to locate them yet. So that's why I don't have the answers on hand. Equal to 10. And let's see. Plus or minus. Yeah, you shouldn't forget that. In this case, it is very, very important. And the reason is because we made an assumption about our node voltages. So if you forget the plus or the minus, our answer is going to turn out to be incorrect. All right, so what values did you get? Again, minus 52, minus 52.9, and VA minus 13 point. So again, this minus is very important. And the reason is VC is equal to 0 volts. So if I plot these 3 dots according to these values, if this is VC, my VB is somewhere here. And my VA is somewhere here. think we are out of time, but I want to make one more point. And that one more point is, now that I have my values for these voltages, you can solve for all voltages and currents in the circuit. Okay. Resistor voltage VR1 is VA minus VC. Automatically have my answer for VA. Sorry, for VR1. Resistor voltage VR23 is VA minus VB. Plug in the node voltages there, and I'll find the resistor voltage there. Then to find the resistor current, IR1, IR23, and IR4, simply take the resistor voltage, apply Ohm's law, and you find that current. So that's how we solve for the unknown voltages and currents in the circuit. I will check my notes and I will continue here in this class, but consider the homework for node voltage analysis as assigned. I have covered the theory in class and I've covered the example. So the due date will be assigned maybe either Saturday or Sunday, but there is no reason for students not to open up that homework. All right, we'll end class here today. We'll pick up here again on Friday.
Professor,
Yes.
for your second equation calculation where you converted from